Good night. In this video, I'm going to continue the topic of differentiation. So last time we introduced a definition and some basic properties, including chain rule. And today our main goal is to prove mean value theorem. Okay, but before that, I want to mention a little bit about like the relationship between differentiability and continuity. So this is the example that I showed last time. It's exactly the same. So this is a counterexample, and it illustrates that given that the function is continuous, it is not differentiable. Here I want to introduce another example where this function is continuous at on R, and it is differentiable on R actually. So after we going over this example, I really want to say is that given, so if we know a function that is continuous, we have no information about whether or not it is differentiable because it could be or it could not be. Okay, so let's quickly go over this example. So fx is defined in this way, and you can check to see some definition for continuity. This is obviously continuous for every x is not equal to 0, right? So we only need to show it is continuous at x is equal to 0, and you can check that using definition. So let's compute the derivative. So if x is not equal to 0, we can use the product rule to compute its derivative directly. And when x is equal to 0, we have to use the derivative definitions here, right? So, and then we plug in the definition for f, and notice that f0 is equal to 0 by the definition of f. Okay, and then after some algebra, we got this expression. And notice that by definition, if this limit exists, that means f prime 0 exists. That means f is differentiable at 0.0. So all we need to do to show that f is differentiable everywhere, which means on the real line, in particular at 0, is to show this limit exists. So there are many ways to show a limit exists. First of all, you can use the very traditional definition epsilon delta, or you can show that using the sequence, right? Limit, so the limit of f fx as x converges to c exists if and only if as for every sequence converges to c, for every sequence xn converges to c, fxn also converges to the same limit, right? But there's other ways, for example, the sandwich rule, if you remember. So here we write this inequality, which is true because sine function is the absolute value of sine function bounded above by 1. So therefore, as t converges to 0, we have this converges to 0. Hence, meanwhile, we also know because of the absolute value, this expression is larger or equal than 0. So it's kind of like sandwiched by 0 and 0. So the only possibility for this to be true is the limit of the expression is equal to 0. But the limit of the absolute value of t times sine 1 over t is equal to 0 implies that limit of t sine 1 over t is equal to 0. This may be so basically what I used here is the limit of an absolute value of some expression is equal to 0 implies the limit of that expression itself is equal to 0. We can do this. It is indeed irrelevant in this topic, but I want to just quickly mention that this works only in complete vector space. So this is not true for all space. We'll mention this more when we go over chapter 5 of full length real analysis. but so far, don't worry about this. Okay, and our goal is to, our goal achieved, right? Because we show that the limit exists and it is equal to 0. Therefore, we have f prime is well defined on R. So we see that the function f is actually differentiable over R. Another thing I want to mention is that we indeed show the differentiation, f is differentiable, right? But we have no information about the continuity of f prime. So for example, in this example, f prime is actually not continuous. You can use definition to check, or you can use, I think the more easier way is to use sequences to check. You can find, you can list 2 different sequences that converges to 0, but the function f prime of those 2 sequences converges into different numbers. Cool. Okay. And then the next thing I want to introduce before we prove the, first we're going to prove the generalized unified theorem, and next we're going to prove as a corollary really quickly the common sense unified theorem. So before I get in touch with the generalized unified theorem, we need to have some definition, and then I need to introduce very important thing that we're going to use a lot in the proof of unified theorem. Okay, so let's look at the definition. So f is a function from x, where here x is a metric space to R. And we say that f has a local maximum at point P. Again, it is local concept, similar as differentiation or continuity. So f has a local maximum at point P in x if there exists delta such that fq smaller or equal than fp for all q in x, such that q is actually in the delta neighborhood of p. So it is dry, and let's look at geometrically. Hopefully that's give you better intuition. So if we have a function f, right, and we are interested about the local maxima. So before you look at the definition, you might intuitively think about the local maxima. It is like even though you know nothing about it, you can guess, right? Local maxima just means that in certain local region, it is the maximum point. And that's exactly what the definition or the geometric interpretation here is saying. So if we have a function f, and then here we have a neighborhood, right? So P is the local maxima if there exists. Notice the quantifier here. There exists a delta, so which means there exists a neighborhood such that for every point in that neighborhood, you evaluate function at point Q, for example. Q is any point in this neighborhood except P. So you evaluate a function at the point Q, and that value should be always smaller or equal than Fp, because Fp should be the maximum, should be the local maximum in the neighborhood. Okay, so after introducing the definition for local maximum, this is a very important thing, and it's short and sweet. So it is the necessary condition for a point to be local maximum. Basically, this is them telling us about if you know a function that has a local, what kind of property can you infer? So f is defined as this way. We assume f has a local maximum at specific point x in this interval AB. And the f is differentiable at x. This is another assumption. So we assume that f has local maximum at a point x in the open interval AB, and f is differentiable at x. Then our claim is that the derivative of f evaluated at x must be 0. And on the other hand, you can also state a theorem. So if f defined in this way and f has a local minimum, if f has local minimum at the point x in the open interval AB, and f is differentiable at x, then f prime of x is equal to 0. So basically, you look at the function of f, right? And you get local maxima, and it's also differentiable at this, then the derivative at this point of function f must be 0. And if it's also true, if p is local minimum, then the derivative of f at point p is also equal to 0, providing local minimum and f is differentiable at this point. Okay, there's some remarks. Well, first of all, so one not challenge, but something we should always keep in mind is whether or not we include or exclude the extremer. So here we don't want to include it, otherwise the statement is not true. Why? Here I give so for example, if we have function f in this way and then on the interval 0, 1, so there if we if we include the close point, the boundary point, then f prime of 1 is equal to 1 is not equal to 0, right? But based on this theorem, f is, first of all, this is a local maximum, right? And f is differentiable at the point x is equal to 1. But f prime is equal to 1 instead of 0. That means the theorem failed. Therefore, we cannot, therefore the condition open interval AB is very important. We can, now let's prove rigorously why the statement, this is true. So let's give a proof. The intuition is very simple, is that, again, you recall the definitions for derivative, right? You're drawing a secant line, and as the point t converges slowly to p, the secant line becomes flat, 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 and it will change the direction. So when it in the process of changing from the positive slope to negative slope, it must be 0 at some moment, right? So that's basically our intuition. And rigorously, let's x to be a point in AB. And by definition of local maximum, recall the definition, right? If there exists a neighborhood, there exists a delta. So fy is smaller or equal than fx because we let x to be the local maxima as the right f has local maximum at x. So here we let x to be the local maximum as our assumption. So for every neighborhood, in the delta neighborhood of x, we have y smaller than fx. And also, we also need to make sure that the neighborhood of X is small enough such that the neighborhood is completely contained in the interval AB. Okay, so now let's consider two cases. The first one is when t is larger than x minus delta, smaller than x. That means t is on the left of, so that means t is in the interval x. It is in the delta interval of x, and t is on the left of x. Then by definition, so let's observe this numerator first. Because fx is the local maxima, t is in the delta neighborhood of x. That means this must be less than 0. And because t is on the left of x, this must be less than 0. Therefore, this is largely equal than 0. And on the other hand, if t is still in the neighborhood of x, and now t is on the right-hand side. And again, because x is local maxima, so this is a smaller equal than 0. But because t is on the right-hand side of x, this is going to be larger equal than 0. Together, this smaller equal than 0. Right? Since f is differentiable, so here we use the second condition. We have the limit of this exists, right? So we know that the left limit is equal to the limit is equal to the right limit. But what do we know? We know every term here is large or equal than 0. And every term here is smaller than 0. Therefore, we know the limit must be larger equal than 0. The limit must be smaller equal than 0. And we also have this inequality. And in order to make sure this inequality holds, what else could it be? I mean, the only possibility for it to hold is that they are. Therefore, we have this conclusion. And this 2 equal to the limit. So therefore, we know the limit must be equal to 0. And the word. You can use the exact same strategy to prove the analog theorem, where we have local minimum instead of local maximum. Cool. So that is very important foundation. We not only use this theorem in the proof of a generalized universal theorem, but also in the theorem that we're going to be introduced later. It is very important, so please keep in mind. Now, let's prove the lemma theorem, the generalized version. So here, keep in mind about closed and open. So if f and g are two functions from a closed interval ab to R, it is continuous on closed interval and it's differentiable on open interval, then we claim there exists x in this open interval such that this equation holds. We'll notice that fb minus fa is really like a constant, does not have any variable. G prime of x is equal to ge minus ga times f prime of x. So we want to show this. Well, if you watch the first video, I mentioned that there is a very common trick, like if you want to prove something, prove about a function or an expression, it is sometimes useful to rewrite the result that you want into a new function and you prove some properties of the function so that it is equivalent with the result you want. So here we want to show equality, right? Well, if we define a new function h to be this, right? And notice that h prime t is equal to this times g prime of t minus this times f prime of t. And then that should remind you immediately about our desired result, right? So that implies that ht, we just need to show h prime x is equal to 0. Then we're done immediately, right? So that is our goal. And we call the thing that we just proved, right? So it is about once you find a function has a local maximum and that function is also differentiable at that point, then we have this very good property. So our desired result is our goal shows this equal to 0, and this looks a lot similar as this, right? So we just need to show H satisfy the condition. Okay. Well, first of all, since Fg are continuous, H is continuous, right? So, and subtraction is continuous function, therefore, H is continuous. And because AB is compact, and we know that the compact continuous function of compact assumes maximum and minimum. So here, H has local maximum on the closed interval AB. Now let's just observe that HA is equal to this expression. HB is equal to the same expression. So we have HA is equal to HB, where A and B are the boundary of the closed interval, or it is the boundary of the domain of F. So now let's, so we already know, so if you now look at this graph, right? So we have HA is equal to HB, and there are actually 4 different possibilities. Let's consider the simplest one, which is H is just a constant function, so it is a flat line everywhere. And then we're done immediately because we have shown before that the constant function has derivative 0. So we're done. Well, what if not? What if it's other cases? Well, without loss of generality, we can actually show there exists a point t in this open interval such that ht is larger than ha or hb. Right. So why do we want to do this, right? So in this case, it's very important to utilize the information that there exists a point t such that ht is large or equal is larger than ha and hb. So let x be the maximum of h on the closed interval AB, and hx equals than ht larger than ha or hb. So thinking this way, so we have shown that HA is equal to HB. And in this specific case, and without loss of generality, we assume there is this point T such that HT is strictly larger than HA or HB. And by definition of the local maximum, since X is local maximum, within that neighborhood, right, it must be the maximum, which means hx is larger or equal than ht. Therefore, and because ht is strictly larger than ha or hb, that means hx must be strictly larger than ha and hb. So why we're doing this? Well, if you recall, so we made an agreement, we're on the same page, right? We want to use the theorem, but we showed it is very important that we satisfy this condition where X is not A or B. It is anywhere, it could be anywhere in this open interval, right? So here we're actually arguing that X cannot be A or B. So that's what I'm doing here. That's what I'm doing here. Okay, so we know X must be in open interval AB, right? And then we the first condition of the theorem in last page is satisfied, and H is also differentiable on closed interval, on open interval AB. This is just because H, the function H, is defined in this way, where each component here is differentiable on open interval AB. So that comes very quickly. Therefore, the condition of the previous theorem is satisfied, and we can use that to obtain the result H prime of X is equal to 0. And therefore, we're done. So we're done with proving the generalized mean-value theorem. And the often used mean-value theorem follows immediately. Why? Because you can just take gx equal to x and then apply the generalized mean-value theorem, and we obtain this. And then we're done. There are, before we end the video, I still want to make sure, I still want to mention some remarks. So again, it's about a closed interval and open interval, and they are very important. So it's very important that f continues on the closed interval AB, because in the proof of generalized mean-value theorem, we actually use the continuity on compact interval to obtain the minimum exists, the existence of a minimum and maximum on this interval. So we indeed use the fact that f is continuous on a closed interval. And then just make sure I also give a counterexample where f is continuous, not continuous on closed interval, but like half open, half closed. And as you can see here, this is equal to 1, 0, so we got 0 here. Okay. The second one is recall that the one of the conditions f must be differential open interval AB. Why is this important? Because we need to use the theorem about the local maximum in the proof of generalized impact theorem. And if you look at that theorem, they require f to be differentiable at x, where x is belong to the open interval AB. Therefore, we must satisfy that f is differentiable on the open interval AB. If it's not, consider this counterexample, the function fx, right? So f1 minus f0 is just equal to, because 1 is larger than 1 over 2, it is equal to 1. And 0 is smaller than 1 over 2. So it's 2 times 0 is equal to 0. So this becomes 1 minus 0 is equal to 1. On the other hand, if you look at the right-hand side, the super right-hand side, f prime x times 1 minus 0 is equal to 1 prime f prime x. What is f prime x? Here I just write it out, right? Right. So, and then this is equal to this. So you can see that neither 2 or 0 is equal to 1. Therefore, the generalized or the mean value theorem does not hold in this case. So it is very important we are mentioning that F is continuous on closed, which is compact interval AB, and F is at least differentiable on open interval AB. Okay, and that's it. So let's write down the outline at the beginning as usual. So the outline here, right? We firstly showed 2 examples, x sine 1 minus x, 1 over x, 0, x is not equal to 0, x is equal to 0. And another example we saw is x squared sine 1 over x squared. X is equal to 0. And then the next thing we talk about is definition of local maximum or local minimum, and the theorem. So the theorem is about local maximum and differentiability. Implies f prime of x is equal to 0. Here, because this is served as a quick reference, I do not choose to write the conditions in detail. They just serve as like refresh of my memory. And then next we prove the generalized inverse, and then the mean inverse. And then we talk about F, right? From AB to R is continuous. It's very important. Closed interval AB and differentiable on open interval. Okay, and I think that's it. Again, thank you for watching, and please let me know if I made any mistake or any typo. Otherwise, we'll see you in the next video.